I'm going to start talking about some of the things that you can do with sugars, and I'm going to go fairly fast here just because you're just learning some of the basics. Some of this should be review or from various biology classes and or organic chemistry. But sugars, it shouldn't be surprising that the sugars can be oxidized since they have the alcohols. Of course, remember, anytime the cheating way just to eyeball something to see if it's being oxidized is if anytime that you're increasing the number of carbon to oxygen bonds, then you're oxidizing it. Anytime you're increasing the number of carbon to hydrogen bonds, you are reducing it. And so sugars, if you think back to Gen Chem, this is where it can get kind of confusing sometimes. They're called reducing sugars if they get oxidized. Because if they are oxidized, that means that they reduced the oxidizing reagent. And so the reducing end of the sugar is the anomeric carbon. Okay, so this is the reducing end of the sugar. This is just called Toland's reagent. It's silver. And it becomes a lactone, which is a cyclic ester. Okay, which is really cool if you ever get to do this in a lab. I've done it once or twice in our lab just as a demonstration in organic chemistry because it's really expensive to use silver, but it forms a mirror. And so if you do it in a test tube, it's like a mirror ball on the end because it is, when the silver gets reduced, it deposits itself on the glass. But silver is expensive, so I don't do it very often. But once again, the anomeric carbon end would be the reducing end of the sugar. That's important whenever we talk about directionality. Remember, the anomeric carbon is also carbon number 1. Or the lower end of the carbon, because sometimes it's carbon number 2, but it's not, it's the lower numbered end. Okay. Sugars can also be reduced, and so the ketones or the aldehyde portion of it can be reduced, and then it becomes an alditol. And this is one example. This is glucose, and this is glucitol, which is also known as sorbitol. What is sorbitol? It's a sweetener. It's also a laxative. If you take it takes a large amount of this, just because a lot of sugar-free gums has sorbitol in it, but I mean, you would have to be like really, 7 packs a day, then you may have some loose bowels. And so, pardon?
The sugar-free gummy bears.
Or the sugar-free, well, the sugar-free gummy bears actually, they come with a warning
Anal leakage.
of anal leakage. That's correct. It's awesome. You ought to read the reviews on Amazon.com, and I'm assuming it's probably because it has a higher concentration of sorbitol than what you would expect. But this is actually from organic chemistry, so for those who have already had organic chemistry, what's a common reducing reagent that you could use here? What is something that you can go from a carbonyl group to an alcohol? You could use Lyle-Heifer, as we like to call it, but what else? What's a more simple, not quite so powerful?
H2 platinum.
And that's correct. So this one, this is hydrogen with it, so it's nickel, but hydrogen with platinum, palladium, nickel, or rhodium. Once again, that just shows an example. Of course, in our body, we don't have those. We use other cofactors such as NADH and FADH2. And then the glycoside is just whenever you replace the alcohol with another bond, and it's called a glycosidic bond. This is saying the anomeric carbon, but you can actually have glycosidic bonds on the other carbons as well. For example, in DNA and RNA, we've seen them that's not on the anomeric carbon. It's one of the others where they make phosphodiester bonds. Technically, if you start off with a 5-membered ring, that's called a furanose, it becomes a furanoside. 6-membered ring where purinose is, so they become pyranosides. So DNA and RNA sugar backbone technically is a furanoside. There's a lot of vocabulary in this chapter. These are just some of the examples, which I realize are kind of difficult to see. Do not memorize all of these. Now, if I say an amino sugar, that means that there's an amino group instead of one of the alcohols. Or an acetyl sugar means an acetyl group's been added on. But don't go through and memorize all these. I would give you a table if I ask you in just a moment. For example, if I asked you to draw a certain type of glycoside bond, I would give you the table or show you like what glucose or mannose or xylose or whatever looks like. But these are just some of the examples. So let me see if I can blow it up. So glucosamine, which you probably have heard people talk about, that's just a glucose. This is glucose, but it's where the 2' alcohol has been replaced by an amino group. So it's glucosamine. And what's glucosamine used for? Surely, especially if you're going to go in the medical profession, you know about glucosamine.
Neurotransmitter?
No. Nope, you can take it as, it's not FDA regulated, you can take it as a supplement, dietary supplement with hydrochondroitin.
It's good for joints.
It's for your joints. So yes, I had to take glucosamine. They're like big old horse pills. Okay, now I wanted to point out once again, since some of you haven't had organic Chem 2 yet, and some of you have probably forgotten, but this is an acetyl group, which you guys had to memorize. The functional groups for acetyl group was just a carbonyl with a methyl. But remember, the nitrogen can be a locant. So it's an N-acetyl group. So this is N-acetyl beta-D glucosamine. Because it was glucosamine, you've added the acetyl group. The acetyl group is through the nitrogen, so the nitrogen becomes a locant. And so that is important because in a little bit we're going to talk about some of these these specialty sugars and how they form large polysaccharides. But there's a whole host of these. Oops. Okay, let me bring this back down. But once again, I would give you this. I do want to point out a couple of things. Let's see. For those who are in capstone course, I wanted to point out the glucouronate because that would be an example similar to what Matthew somewhere was talking about with his I forgot the name of that drug now that was used that was similar to the apricot seed. But remember, it had a carboxylic acid that had been replaced instead of an alcohol. And I just saw that and I thought of it today whenever I was looking through my notes. So some of these we've seen, they are relevant in vivo or pharmaceutically. Okay, the phosphoric ester or phosphoester. We've got two of them to be phosphodiester. Of course, this is similar to DNA. So this one's a pyranoside. And that's all I'm going to say because you can just look through these examples on your own. The amino sugars. I wanted to point these out in particular because these have interesting nicknames. This one they call NAG for N-acetyl beta-D glucosamine, and this one's NAM for N-acetyl uramic acid. And NAM-NAG repeats are really important for bacterial cell walls and for other things too. And so some papers and things will refer to them as NAMs and NAGs. You gotta hear someone give a whole talk on those NAM-NAGs. Quite interesting. This is where I really wanted to focus on more time, put more emphasis on, because like I said, I would give you the key. You just have to be able to put them together. Okay, remember we start off as the hemiacetal for the individual pyranoside or furanoside, and then you just have a condensation reaction and it can form an acetal. But remember, there are two possible ways. It can either start with an alpha and have the alpha be linked to another alcohol over here, or it could have been a beta. And that's going to change the shape of the molecule. Plus, you could have this anomeric, the reducing end of this sugar, and we always talk about the reducing end first, coming, and it could be here, it could be added to carbon number 1, carbon number 2's alcohol, 3, 4, or 6. Okay, and so that's why we have to talk about the linkage. And so this is maltose. Of course, that's a sugar. It's a disaccharide sugar that it does have commercial importance. But the thing of it is its technical term is called alpha-D-glucopyranosol 1,4-glucopyranose. And so because and sometimes they even write it this way. So let me change. the color, to where they'll talk about it being an alpha 1 to 4 linkage versus a beta, 1 to 2, 1 to 4, what have you. And the reason being is it's the carbon number 1 from the glucose connected to the, and it's reducing in the anomeric carbon connected to, it's connected to carbon number 4 of the second one. Oh, so yeah, make sure that, like here, I could have told you that I expected the glucose alpha 1,4 glucose. And by the way, they actually also have, and I'll show you in just a moment, they also have like 3-letter codes for the sugars similar to the amino acids. I don't expect you to memorize them. I will let you know, but glucose is like GLC, galactose is GAL. So I would just tell you like, no, GAL alpha 1,4 glucose or GLC. And I would expect you to be able to put the pieces together. But let's practice. So these are disaccharides, whereas this is sucrose, table sugar. And it's a D-glucose with a D-fructose. And I just want you to take some time to look at it, try to figure out, like, is it, an alpha 1,6, beta 1,2, what kind of linkage it is between the glucose and the fructose. So I'll give you a moment. And they have it drawn here, both in the Hayworth projection and in the more legitimate, chair projection. And this is an alpha 1,2 glycosidic bond. Okay, and the reason why, if you look at fructose, it's symmetrical, but you want to go with the lowest numbered locant. And so that's why here, this is carbon 1, 2, 3, 4, 5, 6, because otherwise it's 1, 2, 3, 4, 5, 6. So that's why we go. Since it's symmetrical and it's not phosphorylated or anything like that, you can just go with the lowest numbered. So it's an alpha 1, 2. Let's do another example. This one's lactose, which some of you are probably intolerant of, and as you get older, you may become more. So I'll give you a moment to look it over and decide. It's a galactose and a glucose.
Can you explain the difference between alpha and beta again for these?
Okay, yes. So once again, and it matters on which carbon we're talking about. We're talking about the one that it's the anomeric carbon. And so this is the anomeric carbon, and there's a little scorpion's tail. And so the original alcohol is pointing on the same side as the scorpion's tail. So same as beta. I memorized it.
Oh, okay.
I memorized it that beta and same both start with consonants, whereas alpha and opposite both start with vowels. And so that's why it's a beta linkage. And if you look at it, like what it really looks like is the chair conformation, it really does kind of look swoopy, I guess. The cartoony way that they do it, it does look swoopy. I know what you mean by swoopy.
Okay, good.
Okay, so here's. Oh, is that the same one that I did before? Okay, whoops. So these are 2 glucoses. So I'll give you a moment to try to figure out what kind of linkage it is. This is what I was talking about before whenever I mentioned the fact that there are like 3-letter codes, just like with amino acids. Do not memorize these. I would give you this table, or I would write it all out. But just to let you know, they also get some places that they give symbols, which the symbols are important because they link them together as little pictures rather than trying to draw everything out all the time. So carbohydrates can form really, really long polysaccharides, and it can either be unbranched or branched, and you can even have multiple branches involved. So these are homopolysaccharides, like the glucose to glucose that we were talking about before, and these would be, heteropolysaccharides, so they don't have to be the same. And you can have this one sugar here, is making bonds to 3 different sugars. And so that's why it's really important whenever we talk about, alpha 1,4 linkage versus a beta, 1,6 or what have you. So these are just some examples on, like I said, I don't know that I'll go through all these here in class today, but you can look at the PowerPoint yourself and read about it in your book. Yes, thank you.
Hey, look, there's this swoopy thing.
That's what, yes, I wanted to show a swoopy. And so the swoopy that she's referring to.
Oh, that's trippy.
Swoopy.
Yeah, it's like they're doing
The wave.
Yeah.
So, okay. But this is cellulose. And so that's why it's beta 1,4s are really, really, really long chains. I mean 2,800 glucoses in a row, but it's the way that it stores its glucose. And, but the reason why it makes it so strong is because remember there's all those alcohols around, and so they can hydrogen bond in between the long fibers. Okay. I wanted to get, it's debranching is what removes it, and the branching enzyme. We actually go over debranching and branching enzymes. Branching enzymes are what puts the branches in. Debranching is what removes the branch. We go over that next semester in metabolic pathways. But I wanted to go just show the example of the cell wall quick. So this was the NAMNAGs that I was talking about before. And so here we have the N-acetylmuramic acid and N-acetylglucosamine and the linkages. And that's what repeats over and over again along the bacterial cell wall that helps give it extra strength. But not only does it do that, but it has ramifications in vivo because of the fact that it's actually the sugars that are expressed in the bacteria, outer cell wall, for those that have cell wall, that or membrane that we can form, a immunological response to. And so this is the way that they come together because they're cross-linked not only by hydrogen, whoops, that's really trippy, hydrogen bonding, that possibilities here, but since it has the acetyl group on there, you can actually use that to stick peptides in. So it's a glycoprotein. And so the way that this is we have the sugar, and then we have this alanine. Let me blow it up. Alanine. I'm going to really keep repeating myself. So it's this tetrapeptide of alanine, glutamine, lysine, and alanine. And this lysine, of course, is really long, right? It has this free amine. Then this free amine can actually be used to form interlinkages. So let's go back. And so each one of those tetrapeptides now has a linkage of 5 glycines in a row. So it's not like a normal protein like we see, because it's got the normal peptide bond, and then hanging off of a lysine that sticks out is another peptide bonding polypeptide that comes down. And so it's like five glycines in a row, and then that connects to the next one. And so you get this interweaving effect within the cell wall, which makes it really, really strong. So it's got sugars and it's got these peptides. That's what this picture is trying to show you. It took me a while the first time I saw this, and so that's why it's called the peptidoglycan cell wall. And so it took me a while because the little balls here are the sugars, and then hanging off the acetyl group is the tetrapeptide, and then hanging off that lysine is 5 glycines, which connects to the next peptide over, which connects to the next one. And so you get this like weaving effect, and that's what gives the bacterium such a strong outer covering. Okay. Are there any questions on this? I would not have you draw this one in particular because it's too intense to try to draw that out. But I do want you to understand where it comes from. Okay. So I'm going to go ahead and end here. I may show you 1 or 2 other ramifications for in vivo. If not, it's already on because we are behind. If not, it's already available on the PowerPoint, and it'll be available in the video as well. Okay, so that way we can start on the next Monday, start on nucleic acids. One of my favorites, of course.